Let's look at the differential and the derivative, because there's a difference between them. Also an example of an application which will apply to a cylinder, and also small increments, that mean small changes, alright, as they apply to partial derivative. Now, differential is really a small change. Example, when you talk about dy by dx is equal to f prime x. If you find that you have y is equal to, say, x squared, dy by dx is equal to 2x, alright? Then dy, let me rewrite that, dy would then be equal to 2x dx. Now, dy by dx is itself a rate of change. This is called the derivative. It's really the slope or gradient of a tangent. It tells you how much y changes as x also changes, alright? It's like rise over run. The change in y is dy, which is the up and down movement, that's the rise. The run is dx, which is the left and right movement, that's run. So it's really the slope or the gradient of a tangent to a curve. That's derivative. Differential is a small change. Dy is a small change in y. How much does it change up or down? Dx is small change in x. How much does it go left or right? Alright? That's the differential and the derivative. Now you remember, like for example, in integration, we would say, what's the integral of x squared dx? Meaning that x is the variable. Dx is a small change in x. Alright? It means that x is the one that's changing. So even if you have x squared, so a x squared, a is just a number in this case because x is the one that's changing. Alright? Other things are constant. So a differential is really a small change, but the derivative is how much one thing is changing as the other changes, which is a slope or a gradient. Right? It gives you the gradient function. Alright, now suppose we consider this. Let me just erase these things that I have here. Alright, we looked at the differential and the derivative a while ago. Let's look at this example now. Suppose you have a cylinder here and you consider the radius r. You also have the height h. Here now, the volume of a cylinder, you remember, is pi r squared h. Alright? Pi r squared h. Now, if you consider both r and h the volume depends on R and H as well. Now suppose you make R constant. R remains constant. Then if you change H, then what you will have is a change in V. Alright? Now, since H is changes, so R is constant and H changes. If you consider that you differentiate and find dV by dH, since H is changing with R constant, then you have a partial differentiation here. You have a partial derivative, right? You have two variables, but you lock one of them for now and change only the other variable. So it's a partial derivative. But as we have seen earlier in previous videos, instead of saying dV by dH and making note that R is constant, what we write is this type of delta V by delta H. It means that we're differentiating V with respect to H while keeping other values constant for now. They can change, right? But you lock them for now and keep them constant. So that's a partial differential coefficient. Delta V by delta H. That's called the partial differential coefficient of V with respect to H. Alright? R, of course, being kept constant for now. So, delta V by delta H, of course, it would be pi r squared. Alright? Because pi is constant, of course, but r is also constant, so but therefore r squared would have to be constant as well. You see that? Now let's rewrite this. Volume is pi r squared H. Suppose you consider locking H for now and make R vary. You make R change, right? Then what you have is the derivative of V with respect to H with, not H. If H is locked and R changes, we have the derivative of V with respect to R with H. Constant for now. Well, you write that, of course, is delta V by delta R. Right? That means the partial derivative of V with respect to R. Right? So, here, what would delta V by delta R be? Well, use the power rule. You bring the power down forward, multiply, and then reduce the old power by 1 to get the new power, as you remember. So it's 2 pi r to the 1 times h. So that's the partial derivative of the volume with respect to the radius, because you make the height h constant. Alright? So here we looked at r being locked constant and h changes. So we found the partial derivative of v with respect to h. That's delta v by delta h. And after that, we lock h and allow r to change. So we're looking at the partial derivative of v with respect to r with h constant. That's delta v by delta r. Alright, so we'll look at what I refer to as small increments in our next video.